In today's ever-increasingly connected world, the need for highly competitive wideband amplifiers is more than ever. Designing wideband amplifiers is challenging, yet modern requirements shoot for the stars. Wideband amplifiers are attractive because they are addressing practical difficulties and needs of the modern communication links. Consider the case of a 5G base station. An ultra-wideband amplifier front end of a base station could support 3G, 4G and 5G signals simultaneously, eliminating the need for separate RF components for each of the protocols. This cuts down the cost and increases the reliability of the network. Hi, this is Burak Güneş. In this video, I will walk you through the basic design and manufacturing steps concerning a wideband amplifier. This amplifier is intended to use in the 1.5 to 2 GHz bandwidth, providing a 10 dB flat gain with the worst case return loss figures of around 13.5 dB. Let's start. Here I present the key requirements of this project. First, base and collector pins should be fed from the same supply. Also, a return loss of at least 12 dB is a necessity, since then it could be used in cascade configurations. Last but not least, 10 dB gain in the 500 MHz band. Here you see the topology used. Wideband matching circuits match the base and the collector of the amplifier to 50 ohm lines. DC biasing circuit and the stabilization network work together to ensure a smooth, stable operation. It is where the decoupling capacitors are. Now continuing with the DC biasing circuit. DC operating point is chosen to ensure that a high gain was available at the output. We can find this point by referring to the current cutoff plot given in the datasheet. Here you see the biasing circuitry. Two resistors form the low beta dependence biasing circuit. This is a critical aspect of the design because beta is a function of the collector current, whereas we design our circuits thinking that the beta will be constant. We have completed discussing the DC segment of the circuit. Now let's continue with the matching circuits. Input matching circuit transforms the impedance seen at the input of the amplifier. This is accomplished by the use of one series RC circuit and a shunt RL circuit. For the output matching, we can get away with using a simpler topology. There are no lumped components in this circuit. We have completed the design of the amplifier. Let's now move on to the PCB layout of the amplifier. Here, input matching and output matching segments are highlighted over the PCB. The DC segment of the amplifier is more populated. There are many decoupling capacitors, resistors, RF chokes that are eventually connected to the base and the collector of the transistor. One thing missing in those figures were the vias. They are critical in the amplifier design. Note the placement of the emitter vias. They are just next to the emitter pins so as to provide a low inductance path towards the ground. And finally, manufacturing and verification. This figure displays the completed amplifier connected to a vector network analyzer. First, I will discuss the DC measurements, then small signal linear measurements. I will conclude with the nonlinearity characterization. DC measurement result is shown. There is nearly a 10% difference between the large signal model's predictions and the measurement. After elaborate checking of the lumped resistor values using a multimeter, I concluded that this is a device-level deviation from the manufacturing specs. Next comes the small signal measurements. I promised 10 dB gain, yet measurements show much less. On the other hand, up until 1.8 GHz, gain is flat as desired. S11 measurements reveals the source of the problem with the low gain at higher frequencies. Amplifier is not matched to a 50 ohms line properly at higher frequencies. S22 measurements demonstrate that output matching is reasonably achieved. Noise figure of 4.72 dB is quite large. However, this is again reasonable because the design wasn't motivated by achieving low noise characteristics. Finding the 1 dB completion point of the amplifier is critical. This figure demonstrates the linearity of the amplifier. By sweeping the power from minus 25 dBm to 10 dBm using a vector network analyzer, we can reduce the 1 dB compression point by linear extrapolation. For this case, we can argue that up until 24 dBm output power, this amplifier will stay in the quasi-linear region. Note that plus 20 dB figure comes from the 20 dB attenuator used in the measurement setup. And finally, OIP3. This figure arises out of the assumption that the amplifier is weakly nonlinear and relates the magnitude of the intermodulation products to fundamental tones. To measure this, two signal sources, one outputting 1.75 GHz and the other one giving 1.75 GHz plus 1 MHz were used. Then we view the output using a spectrum analyzer. In practice, finding the exact OIP3 point is difficult if not impossible. For this reason, we will extrapolate the results at lower power levels. Here in this formula, P1 and P2 refers to measurements of the harmonics and at the fundamental at the same input power. You can observe the spectrum analyzer screen yourself. Intermodulation products are at a level 70 dB lower than the fundamental. Therefore, OIP3 figure is equal to 24.75 dBm. Thank you so much for your patience.